Modules. If you quit from the Python interpreter and enter it again, the definitions you have made, functions and variables, are lost. Therefore, if you want to write a somewhat longer program, you are better off using a text editor to prepare the input for the interpreter and running it with that file as input instead. A text editor like Notepad, any simple thing that you can put text into, will work. This is known as creating a script. As your program gets longer, you may want to split it into several files for easier maintenance. You may also want to use a handy function that you've written in several programs without copying its definition into each one. To support this, Python has a way to put definitions in a file and use them in a script or in an interactive instance of the interpreter. Such a file is called a module. Definitions from a module can be imported into other modules or into the main module, the collection of variables that you have access to in a script executed at the top level and in calculator mode. A module is a file containing Python definitions and statements. The file name is the module name with the suffix .py appended. Within a module, the module's name, as a string, is available as the value of the global variable __name__. For instance, use your favorite text editor to create a file called fibo.py in the current directory with the following contents. It's a Fibonacci numbers module, because they love Fibonacci for examples. Defining this function fib, which takes in, this has this one parameter in. It sets the values of two variables, a and b, simultaneously equal to 0 and 1. And then it begins this while loop, which checks while a is less than n, print a, use space, a white space, as the endpoint. There's the thing marking each step. And then simultaneously update the values of variables a and b to the values b and a plus b, respectively, and print. We've seen something, I think we've seen this exact logic before in the tutorial. It's just a simple way to generate a series, a Fibonacci series. And here's a second, fib2, which takes one argument, similarly, and will return a Fibonacci series up to n, similarly, but just from a slightly different approach. They've made an empty list called result, into which they will append the results of this logic, right? And then return that list. Now enter the Python interpreter and import this module with the following command. Import fibo. This does not add the names of the functions defined in fibo directly to the current namespace, and we haven't gotten to namespaces yet, but we will. It only adds the module name fibo there. Using the module name, you can access the functions therein, though. It's like a little portal. So, say, after you have imported it, if you said fibo.fib 1000, pass that in as an argument, then you'd generate a Fibonacci series up to but not including 1000. Do the same thing with... Wow, that was real time, folks. The screen just turning black for no reason. I'm poor, that's why I'm trying to learn how to program. And here, see, this used the white space at the end of each iteration. That's why you got a space in between them, like that. Here's fibo.fib2 with 100 passed in. We'll generate this, and filling this list result, right? And if we check the namespace, fibo.__name__, it will return just fibo. If you intend to use a function often, you can assign it to a local name. So we could take fibo.fib, assign it to fib, and then later we can just call the variable fib, pass in arguments like this here, and we see just as earlier. More on modules. A module can contain executable statements as well as function definitions. These statements are intended to initialize the module. They are executed only the first time the module name is encountered in an import statement. They are also run if the file is executed as a script. Each module has its own private namespace, which is used as the global namespace by all functions defined in the module. Thus, the author of a module can use global variables in the module without worrying about accidental clashes with a user's global variables. On the other hand, if you know what you are doing, you can touch a module's global variables with the same notation used to refer to its functions, modName.itemName. Modules can import other modules. It is customary but not required to place all import statements at the beginning of a module, or script for that matter. The imported module names, if placed at the top level of a module, outside any functions or classes, are added to the module's global namespace. There is a variant of the import statement that imports names from a module directly into the importing module's namespace. For example, if we said, from Fibo import specifically fib and comma fib2, then from there, we can just call fib, without having to set it specifically to fib like that. This does not introduce the module name from which the imports are taken in the local namespace. So in the example, Fibo is not defined. There is even a variant to import all names that a module defines. From Fibo import star, which we've seen before. It's like unpacking, similarly here. And since we've imported star, we've got everything the Fibo contains, and we can use it from there on out. This imports all names except those beginning with an underscore. In most cases, Python programmers do not use this facility since it introduces an unknown set of names into the interpreter, possibly hiding some things you have already defined. Note that in general, the practice of importing star from a module or package is frowned upon, since it often causes poorly readable code. However, it is okay to use it to save typing in interactive sessions. If the module name is followed by as, then the name following as is bound directly to the imported module. So import Fibo as fib, then we call fib.fib. This is effectively importing the module in the same way that import Fibo will do, with the only difference of it being available as fib? That's oddly worded, or am I missing something? It can also be used when utilizing from, with similar effects. So from Fibo, import fib as Fibonacci, then you can just call Fibonacci. It'll function the same way as fib. For efficiency reasons, each module is only imported once per interpreter session. Therefore, if you change your modules, you must restart the interpreter. Or if it is just one module you want to test interactively, use importlib.reload, e.g. import lib, import lib.reload, and parenthetically module name. Executing modules as scripts. When you run a Python module with Python space fibo.py space argument, for instance, the code in the module will be executed just as if you imported it, but with the dunder name set to the dunder main. That means that by adding this code at the end of your module, if underscore underscore name underscore underscore equal the string underscore underscore main underscore underscore colon, import sys fib of int of sys.argv at 1. Bear with me. You can make the file usable as a script as well as an importable module because the code that parses the command line only runs if the module is executed as the main file. So say python fibo.py argument 50 and bada bing bada boom. If the module is imported, the code is not run. Import Fibo, nothing happens yet if you just say that. I mean, it's accessible now in the rest of the code, but you're not making anything happen just yet. This is often used either to provide a convenient user interface to a module or for testing purposes. Running the module as a script executes a test suite. Now, module search path. When a module named spam is imported, the interpreter first searches for a built-in module with that name. That's where it's going to look first, built-in. These module names are listed in sys.builtin_module_names. If not found, it then searches for a file named spam.py in a list of directories given by the variable sys.path. Sys.path is initialized from these locations. So the sys.path is your file name, like a file name pathway. It's the map that it's got, the list of steps it's going to do to try and find the thing. The directory containing the input script, or the current directory when no file is specified. Then Python path, a list of directory names with the same syntax as the shell variable path. Then the installation-dependent default, by convention including a site packages directory handled by the site module. More details are at the initialization of the sys.path module search path. On file systems which support symlinks, the directory containing the input script is calculated after the symlink is followed. Jesus. In other words, the directory containing the symlink is not added to the module search path. After initialization, Python programs can modify sys.path. The directory containing the script being run is placed at the beginning of the search path, ahead of the standard library path. This means that scripts in that directory will be loaded instead of modules of the same name in the library directory. This is an error unless the replacement is intended. See section Standard Modules for more information. Compiled Python files. Now, to speed up loading modules, Python caches the compiled version of each module in the __pycache__ directory under the name module.version.pyc, where the version encodes the format of the compiled file. It generally contains the Python version number. For example, in CPython release 3.3, the compiled version of spam.py would be cached as __pycache_/spam.cpython-33.pyc. This naming convention allows compiled modules from different releases and different versions of Python to coexist. Python checks the modification date of the source against the compiled version to see if it's out of date and needs to be recompiled. This is a completely automatic process. Also, the compiled modules are platform independent, so the same library can be shared among systems with different architectures. And there's a note here, if you're not familiar with what this means to compile something, that because Python is an interpreted language, the interpreter checks and figures out each chunk of code at when it's running, right at that. And that's not universal among programming languages. Many of them are compiled, where the code that you write, you pass it to the compiler, and it goes through all of your human-written code and translates it into machine code, so that when you actually run the program, it's already done the work of translating your human-written stuff into machine code. Because an interpreter only translates at runtime as needed. And so compiling something makes it run faster, and a very oversimplified way to describe that, but generally speaking, to compile a file means to take care of the translation work ahead of time, so that you've just got something the computer can directly understand, because of course all programming languages, I guess besides like assembly, or especially Python, is extremely high level and abstracted. The computer can't do shit with that until it has been interpreted. Let's see here. Python does not check the cache in two circumstances. First, it always recompiles and does not store the result for the module that's loaded directly from the command line. Second, it does not check the cache if there is no source module. To support a non-source, compiled-only distribution, the compiled module must be in the source directory, and there must not be a source module. So some tips for experts. A little early on for this, buddy. You can use the -0 or -00 switches on the Python command to reduce the size of a compiled module. The -0 switch removes assert statements. The -00 switch removes both assert statements and doc strings. Since some programs may rely on having these available, you should only use this option if you know what you're doing. Optimized modules have an opt-tag and are usually smaller. Future releases may change the effects of optimization. A program doesn't run any faster when it is read from a .pyc file than when it is read from a .py file. That's right. That's a mistake I made in how I was describing that earlier. The only thing that's faster about .pyc files is the speed with which they are loaded. The module compile all can create .pyc files for all modules in a directory. There is more detail on this process, including a flowchart of the decisions, in PEP 3147. Now, standard modules. Python comes with a library of standard modules described in a separate document, the Python library reference. Library reference hereafter. Some modules are built into the interpreter. These provide access to operations that are not part of the core of the language but are nevertheless built in, either for efficiency or to provide access to operating system primitives such as system calls. The set of such modules is a configuration option which also depends on the underlying platform. For example, the WinReg module is only provided on Windows systems. One particular module deserves some attention, sys, S-Y-S, which is built into every Python interpreter. The variables sys.ps1 and sys.ps2 define the strings used as primary and secondary prompts. So if we import sys and we update and we check what sys.ps1 looks like, here's the primary prompt with which we are familiar. If we check what sys.ps2 looks like, here's the secondary prompt with which we are familiar. But if we update the value of the primary prompt to the string C chevron space, then thereafter the primary prompt will look like this, C chevron space. Why you would do that? I don't know. I straight up have no idea. These two variables are only defined if the interpreter is in interactive mode. The variable sys.path is a list of strings that determines the interpreter's search path for modules. It is initialized, that's a better way to say what I tried to say earlier. It is initialized to a default path taken from the environment variable Python path, or from a built-in default if Python path is not set. You can modify it using standard list operations. So say if we import sys, and we affected sys.path using the .append method, and this argument here that is little pathway, that's going to modify the path that it uses to search for modules. The dir function, or dir, directory. The built-in function dir is used to find out which names a module defines. It returns a sorted list of strings. So we call dir on Phoebo, we just get a couple things. If we call dir on sys, we get a million freaking things. Without arguments, directory lists the names you have defined currently. So we just call dir, then we just get stuff in our little local space, including what we just imported. Note that it lists all types of names, variables, modules, functions, etc. Directory does not list the names of built-in functions and variables. If you want a list of those, they are defined in the standard module built-ins. So you could import built-ins, call dir on built-ins, and then you will get a whole lot of things. Packages are a way of structuring Python's module namespace by using dotted module names. For example, the module name a.b designates a submodule named b in a package named a. Just like the use of modules saves the authors of different modules from having to worry about each other's global variable names, the use of dotted module names saves the authors of multi-module packages, like NumPy or Pillow, from having to worry about each other's module names. Suppose you want to design a collection of modules, a package, for the uniform handling of sound files and sound data. There are many different sound file formats, usually recognized by their extension, for example, .wav, .aiff, .au. So, You may need to create and maintain a growing collection of modules for the conversion between the various file formats. There are also many different operations you might want to perform on sound data, such as mixing, adding echo, applying an equalizer function, creating an artificial stereo effect, distortion, all the way to hell. So in addition, you will be writing a never-ending stream of modules to perform these operations. Here's a possible structure for your package, expressed in terms of a hierarchical file system. Sound is the top-level package, with the init.py initializing the sound package. And here we got formats, effects, and filters are all sub-packages for file format. This is the sub-package for file format conversions. This is for sound effects, this is for filters. But the point is that these are all sub-packages within this package which has been initialized. When importing the package, Python searches through the directories on sys.path looking for the package subdirectory. The dunder init.py files are required to make Python treat directories containing the file as packages, unless using a namespace package. A relatively advanced feature, so let's forget completely about it for now. This prevents directories with a common name, such as string, from unintentionally hiding, don't name it string, from unintentionally hiding valid modules that occur later on the module search path. In the simplest case, init.py can just be an empty file, but it can also execute initialization code for the package or set the all dunder variable described later. Users of the package can import individual modules from the package. For instance, you could go import sound.effects.echo, and that is, you're laying out the pathway to follow. Sound.effects.echo. This loads the submodule sound.effects.echo. You don't say. It must be referenced with its full name, just like me. Sound.effects.echo.echo filter with passed in input, output, keyword argument for delay, and a keyword argument for attenuation. An alternative way of importing the submodule is from sound.effects import echo. So, telling it to find your way through here to here, and then from here, here's the individual thing I want you to import. Same thing. This also loads the submodule echo and makes it available without its package prefix, so it can be used as follows. You can just echo.echo filter. You don't have to include this whole pathway when using it, right? Yet another variation is to import the desired function or variable directly. So this goes even one step further, tells it to find your way through sound, to effects, to echo, and then import the one function or variable they're trying to get. And again, this loads the submodule echo, but it makes its function echo filter directly available. So we have even less that we have to say when using it. We can just straight up use just that. Note that when using from package import item, the item can be either a submodule or subpackage of the package or some other name defined in the package like a function, class, or variable. The import statement first tests whether the item is defined in the package, and if not, it assumes it is a module and attempts to load it. Son of a gun. Sorry, my chair started talking. Okay. If it fails to find it, an import error exception is raised. What a wonderfully descriptive, self-evident name. Contrarily, when using syntax like import item dot subitem dot sub-item, each item except for the last must be a package. The last item can be a module or a package, but it can't be a class or function or variable defined in the previous item. Importing star from a package. Now what happens when the user writes from sound.effects import star? Ideally, One would hope that this somehow goes out to the file system, finds which submodules are present in the package, and imports them all. This could take a long time, and importing submodules might have unwanted side effects that should only happen when the submodule is explicitly imported. The only solution is for the package author to provide an explicit index of the package. The import statement uses the following convention. If a package is __init___.py code, defines a list named __all__. It is taken to be the list of module names that should be imported when from package import star is encountered. It is up to the package author to keep this list up to date when a new version of the package is released. Package authors may also decide not to support it if they don't see a use for importing star from their package. For example, the file sound/effects/init.py could contain the following code. The dunder all set equal to the list, echo, surround, and reverse. Now this would mean that from sound.effects import star would import specifically these three things named, these three named submodules of the sound.effects package. Be aware that submodules might become shadowed by locally defined names. For example, if you added a reverse function to the sound/effects/init.py file, the from sound.effects import star would only import the two submodules echo and surround, but not the reverse submodule because it is shadowed by the locally defined reverse function. Okay, so here we've got this on 3 lines instead. And this, see now it's referring to the reverse function now. See, we define a reverse function that's going to shadow the reverse.py submodule. This is just a random ass. It's not important to go over this code. The point is what will happen if you define a function there. If __all__ is not defined, the statement from sound.effects import star does not import all submodules from the package sound.effects into the current namespace. It only ensures that the package sound.effects has been imported, possibly running any initialization code in init.py, and then imports whatever names are defined in the package. This includes any names defined and submodules explicitly loaded by init.py. It also includes any submodules of the package that were explicitly loaded by previous import statements. Consider this code. Import sound.effects.echo, import sound.effects.surround, and from sound.effects import star. Now, in this example, the echo and surround modules are imported in the current namespace because they are defined in the sound.effects package when the from import statement is executed. This also works when the dunder all is defined. Although certain modules are designed to export only names that follow certain patterns when you use import star, it is still considered bad practice in production code. Remember, there is nothing wrong with using from package import specific _submodule. In fact, this is the recommended notation unless the importing module needs to use submodules with the same name from different packages. Intra-package references. When packages are structured into subpackages, as with the sound package in the example, you can use absolute imports to refer to submodules of siblings packages. For example, if the module sound.filters.vocoder needs to use the echo module in the sound.effects package, it can use from sound.effects import echo. You can also write relative imports with the from module import name form of import statements. These imports use leading dots to indicate the current and parent packages involved in the relative import. From the surround module, for example, you might use from dot import echo, from dot import formats, and from dot filters import equalizer. And just to be helpful, I'm going to scroll back up take a look at this example here, pause the video, and you can see what this is doing. In this example, the echo and surround modules are imported in the current namespace because they are defined in the sound.effects package when the from ... import statement is executed. Oh my god, I already read this. I haven't fucking scrolled down enough. Jesus. It's a good thing nobody's watching these. Note that relative imports are based on the name of the current module. Since the name of the main module is always main, modules intended for use as the main module of a Python application must always use absolute imports. Packages in multiple directories. Packages support one more special attribute, __path__. This is initialized to be a list containing the name of the directory holding the packages init.py before the code in that file is executed. This variable can be modified. Doing so affects future searches for modules and subpackages contained in the package. While this feature is not often needed, it can be used to extend the set of modules found in a package. Footnote. In fact, function definitions are also statements that are executed. The execution of a module-level function definition adds the function name to the module's global namespace. It's fun. It's like memento or something reading this tutorial because we go over things before you get to the section that explains them. But good luck. We will get to namespaces eventually.